Have you ever looked up at a skyscraper and just thought, wow, how did they even build that? Now imagine building not just any skyscraper, but the tallest one in the entire world. It sounds like something out of a science fiction movie, right? But today, we're going to break down exactly how humanity achieves these incredible feats of engineering. We're talking about a journey that pushes the limits of physics, materials, science, and human ingenuity. From digging deep into the earth to reaching for the clouds, this is the story of how to build the highest building on the planet. Before a single shovel hits the ground, the most crucial work begins. It all starts with the foundation. You can't build a mile-high structure on shaky ground. Engineers spend months, sometimes years, studying the geology of the site. They drill deep into the earth to take core samples, analyzing every layer of soil and rock. They need to find bedrock, the solid rock layer that can support the immense weight of the skyscraper. For the Burj Khalifa in Dubai, the world's current tallest building, the soil was a mix of weak sandstone and siltstone. Not exactly ideal. So, what did they do? They drilled 192 massive concrete piles, each 1.5 meters in diameter, and sunk them over 50 meters deep into the ground. That's like burying a 15-story building upside down, just to create a stable base. These piles work through friction, essentially gripping the surrounding soil and rock to anchor the building. On top of these piles, they poured a colossal concrete slab, called a raft foundation, that's nearly 4 meters thick. This combination distributes the building's enormous weight, preventing it from sinking or tilting. So, the first step to building high is to go deep. With the foundation set, it's time to go vertical. And for that, you need a skeleton, a super strong structural frame. Modern skyscrapers have moved beyond the traditional steel frames you might picture. The tallest buildings today, like the Burj Khalifa and the upcoming Jeddah Tower, use a buttressed core system. Imagine a massive, super strong hexagonal or V-shaped concrete column running right through the center of the building. This is the core. It houses the elevators, stairwells, and all the mechanical guts of the building. Then, from this central core, you have 3 wings, or buttresses, that branch out. This chape is incredibly stable. It resists twisting forces from the wind, which is a skyscraper's greatest enemy. As the building gets taller, the wings step back, making the building's profile narrower. This not only creates an elegant tapering design, but also helps to confuse the wind. Let's talk more about that wind. It's a relentless force. At 1,000 meters up, wind speeds can be ferocious. If a building were just a simple, flat-sided box, the wind would create powerful vortices, or swirling eddies of air on the downwind side. These vortices can cause the building to sway back and forth in a regular rhythm, a phenomenon called resonance. If the swaying matches the building's natural frequency, it can be catastrophic. That's why the tapering, spiraling, and irregular shapes of modern skyscrapers are so important. They break up the flow of the wind, preventing these powerful vortices from forming. The building's design itself becomes a tool to manage the aerodynamic forces, ensuring it stands firm even in a storm. So we have the foundation and the shape. Now, what do we build it with? The material of choice for super tall structures is reinforced concrete. But this isn't the same concrete you see in your driveway. This is high-strength, high-performance concrete. It's a special mix with additives that make it incredibly strong and durable. But concrete's strength is in compression when it's being squeezed. It's weak in tension when it's being pulled. That's where steel reinforcement bars, or rebar, come in. Thousands of tons of steel rebar are embedded within the concrete, creating a composite material that can handle both squeezing and pulling forces. The steel gives the concrete the tensile strength it needs to resist bending from wind or seismic activity. Together, they form the muscle of the skyscraper. Now for one of the biggest logistical challenges. How do you get all this concrete half a mile into the sky? You can't just use a crane and a bucket. The answer is a series of incredibly powerful pumps. For the Burj Khalifa, a single pump at the base pushed the concrete mix through a high-pressure steel pipe all the way up to a record-breaking height of over 600 meters. This was a world first. To achieve this, the concrete mix had to be perfect. Too thick, and it would clog the pipes too thin, and the components would separate under the immense pressure. They even had to pour the concrete at night when the desert temperatures were cooler to ensure it set properly. It's a delicate, high-stakes operation where one mistake could bring the entire process to a halt. As the core of the building rises, another marvel of engineering climbs with it. The cranes, you've probably seen them, perched precariously on top of unfinished skyscrapers. How do they get there? They build themselves. A crane is first erected next to the building. As the building grows, the crane uses its own lifting power to add new sections to its mast, essentially jumping up the side of the structure once it can't go any higher from the outside. Smaller cranes are lifted to the top floors. These cranes then continue the construction, and even help to dismantle the larger crane below. Eventually, you're left with a very small crane at the very top, which can be disassembled, taken down in a service elevator, and the final spire is often jacked up into place from inside the building. It's a carefully choreographed ballet of machinery, hundreds of meters in the air. While the structure is going up, another critical component is being installed, the outrigger and belt truss systems. Think of these as the building's shoulder and hip joints. At several points up the building, massive steel or concrete trusses connect the central core to the outer columns. These are the outriggers. They act like giant levers, transferring some of the lateral load from the wind from the core to the outer columns, engaging the entire width of the building and resisting the sideways force. This makes the structure incredibly stiff and stable. Belt trusses often wrap around the perimeter of the building at the same levels as the outriggers, tying all the outer columns together and further distributing the loads. It's a hidden system, but it's essential for the building's stability. And what about swaying? No matter how well designed, every tall building will sway in the wind. The goal is to manage that sway so that the people inside don't feel it. You don't want your office on the 150th floor feeling like a ship in a storm. This is where the tuned mass damper comes in. A tuned mass damper is a giant pendulum, a massive block of steel or concrete, weighing hundreds of tons, suspended near the top of the building. It's connected to the structure with springs and shock absorbers. When the wind pushes the building one way, the damper, due to its inertia, swings in the opposite direction. This counteracts the motion of the building, damping the vibrations and significantly reducing the sway. The Taipei 101 Tower has a famous one that's a tourist attraction in itself, a giant golden sphere visible from an indoor observatory. Building the world's tallest building is more than just stacking floors. It's a symphony of science, an orchestration of logistics, and a testament to human ambition. It requires digging deep, mastering the wind, creating new materials, and inventing new construction techniques. From the invisible foundation buried deep in the earth to the gleaming spire that touches the sky, every single element is a solution to a mind-boggling challenge. The next time you see a superioral skyscraper, you'll know that you're not just looking at a building. You're looking at one of the greatest achievements of modern engineering. Thanks for watching, and if you enjoyed this deep dive, don't forget to like, subscribe, and hit that bell icon for more stories from the world of engineering.